Okay. So what I'm discussing, where I stopped was I wanted to actually develop a framework for calculating stuff like this, which is a correlation function. Right? We want to calculate something like this, and as I had indicated to you yesterday, if you look at that paper of Antoine's I had showed you on the first day, and look at the appendix of that, there is an algorithm for Quantum Monte Carlo that is given there, and that will actually try to calculate things like this, and then analytically and get the values of these quantities at the Matsubara frequencies, and then analytically continue that to real frequencies, and from there you can Fourier transform that to time domain and get whatever time dependent responses you want. Okay, so that's why we are doing all this, and for doing this we would like to put the partition function in a framework of a path integral. That's what we want to do. Okay, and the motivation for that I just gave you last time itself. So the partition function is trace over this Boltzmann matrix, and this quantity is the trace you take a complete set of states, for example the eigenstates of the Hamiltonian, and you just take this object and then sum over all the states. Okay, this object can be interpreted as an amplitude for propagation from state n, let me start at time t equal to 0, and then going all the way to minus I beta. Okay, so this can be interpreted like that. Okay, so what we will then say is that there is a formula for this kind of amplitude given by Feynman as a path integral. So what we would like to do is we would like to take the partition function and write it out as a path integral. This is what we want to do. Okay, and for that we need the classical action of this system. So what is the difficulty in getting the classical action? So let me show you that by considering a single orbital, right? Imagine that there's some single orbital here, and the Hamiltonian for that we can just write down some energy of that orbital, and there is this state. Okay, all right. And what is the Hilbert space of the system? So this is the second quantized way of looking at it. If you want to think in terms of the occupation numbers, the Hilbert space is spanned by these two states, namely no particle and one particle. Okay, that's all that's there in this world. Nothing else is there in this world. Okay, all right. Now what I would like to do is, I would like to see whether I can find some states which are what I will call as classical states. Like for example, if I have a harmonic oscillator, as we discussed in the last meeting, the coherent states are the classical states. So the natural thing to do then would be just try imitating the coherent states here, right? Okay, so let's say that there is a coherent state which is described by, let's say, complex number phi. Let's say it's there. So what equation will it satisfy? It will satisfy the following equation, just by analogy with the harmonic oscillator, for example, a bosonic system. Okay, now this already gives you a problem, right? And the problem is the following: if I do another C on this, and if this were a C number, complex number, then the second C will slide through that, and then you would hit this, right? And that would give me phi square. And this object, because it's fermionic, is already 0, right? So that would mean that phi square is 0, and then there's nothing for us to do actually, right? Okay, so there's a problem. Okay, I will show you that the problem is not just this. There's actually a bigger problem. So this guy is a solitary chap here. So why don't we just add a partner to that? Let's add a second orbital, right? And let's say that's also at the same energy E0. So let me call this as 1 and 2. Since that is at the same energy E0, I don't need to worry about the absolute value of energy. Just throw that away and write a Hamiltonian that looks like this, some hopping, let's say. Actually, I don't need the Hamiltonian for the description, but I'm just motivating it. So you can imagine this is like a hydrogen molecule or something like that. So that's the story. Okay, now then what will I do? I will want to have these two states and then associated coherent states. So I could define, for example, a coherent state which is phi 1, phi 2 associated with this problem. And what is the definition of phi 1 and phi 2? If I hit this with C1, I will get this phi 1 times phi 1, phi 2. Right? So you can imagine that these are like coupled harmonic oscillators if you want to have a bosonic analog for this. And then there is a set of set of number states associated with this state and a set of number states associated with that state, and this is the spring coupling the two oscillators, if you wish. If you want to visualize it like that, you can do that. Okay, now let me hit this with C2, and if I hit this with C2, well, I would just get, sorry, phi 2 times phi 1, phi 2. This is what I would get. Okay, nothing much has happened. All right. Now what we will do is, if I hit this again with C1 again, I will again get this problem that phi 1 square has to be 0. Right? So this necessarily means that phi 1 square has to be equal to 0. And by the same token, phi 2 square also has to be 0. Okay, good. Now let's do something else. I'm going to hit this with C2 and see what happens. So I'm going to hit the first line with C2. So this is C2, C1, phi 1, phi 2. And we have posited that this object is a C number. So C2 will slide through that, right? So what will I get? I'll get phi 1, C2, phi 1, phi 2. And by definition of this quantity, this is phi 1, phi 2, phi 1, phi 2, like this. Good? Okay. Now, I will take the second equation and hit that with C1. Okay? C1, C2, phi 1, phi 2. This object is phi 2 times this. If phi 2 is a C number, C1 will slide through. Okay, now this is getting a little boring, so let me just do it. Okay? All right. Now what I'm going to do is, I'm going to add these two equations. Right? So if I add these two equations, what will I get? I'll get C1, C2 plus C2, C1 right? Correct? But what is this quantity? But that is 0, right? It's anti-commutator, correct? So, and because they're fermionic, it is 0. And that means that this object has to be 0. So do you know anything? Do you know anything that that actually anti-commutes by multiplication? I heard that. That's the correct answer actually. Cross product, right? A cross B plus B cross A is equal to 0. Okay, so this could be some cross product like things. Okay, it could be. Okay. So instead of getting into that, what it can be, I'm simply going to appeal to a different line of argument. So way back in 6th standard or 7th standard, I think these days it's maybe 1st standard, because I've heard parents complaining that people are not being taught algebraic geometry in kindergarten. So, okay, all right. So you have encountered this quantity, which is I, right? And you just took it, somebody said there's something called I, and then it's square root of -1. And then you defined even complex numbers. How? You said that, oh, I'll take a real number, and then I will take a complex number and make some object like this. And then you even have defined multiplication of Z1 and Z2 and so on. So there is an algebra that you have developed with these kind of things. So this algebra has two objects. It has this object which is 1 and I. And what can I do? I can stretch 1 by any real number. I can stretch I by any real number. I can add them and I can make composite numbers out of these. That's what we call as complex numbers. Okay. So now what I'm going to do is, associated with these one particle states that we have, I'm simply going to say, just say, that there are some numbers called phi 1 and phi 2, and I'm also going to bring their complex partners, phi 1, phi 2, phi 1 star, phi 2 star. Now what? For example, if A is a complex number, then I can define something called A phi I, or I can define something like A phi star I. Okay, And the rules that these guys follow for multiplication are the most important ones. So they follow the following rules. Phi I, phi j plus phi j, phi I equal to 0. Okay. I also have additional rules. Phi I, phi star j plus phi star j, phi I equal to 0. And then phi I star, phi j star plus phi star j star I equal to 0. I have these rules. Okay. So they form the algebra. They define the algebra form. So for example, complex numbers, if I had these elements of the complex numbers, so these are the analog of phi and phi star if you like. So this square will be 1, this times this will be I, and so on. You know, and I square is minus 1. That's the algebra. Those are the rules. Okay. Now you can actually extend this to have I, j, k and so on. They're called quaternions. Some of you may be familiar with this. So you can actually extend this thing to be not just one I, but it can have many other things there. Okay. So there are various ways of constructing algebras, right? And this is one of them. Okay. Now what I can do within this set of rules, I can also define products of these things, right? So for example, I can define something like phi 1, phi 2, phi 3 star. That's perfectly fine. But there is no meaning in talking about phi 1, phi 2, phi 2 because that's already 0. Because this fellow will tell you that phi 2 square is 0. Right? So if I give you this many set of objects, right, how many distinct products can you obtain? How many distinct products can you obtain? That's easy, right? What you can do is you can either choose one or not choose it, right? So it's 2 power 4. If you don't choose anything, that's 1. That's this 1, right? You see what I'm saying? No. So suppose let me show you the example with just 2 of them. Let's say there is phi and phi star. What are all the possible things you can do? The set of things that will span the space of the composite objects, that is things like complex numbers, would be something like this. I'll have 1, the number 1, and then I'll have phi, I'll have phi star, and then I'll have phi star phi. So anything in the space is a linear combination of a complex number plus a complex number, another complex number stretching this, and so on. Okay? So now, if I have 4 of these guys, how many are there? It's easy, it's 2 power 4. Right? Because in the product you can either keep it or not keep it. Right? Okay. So that's the set of all things you can construct out of this. Okay? So you've understood what so these are what are called as generators, and this algebra is called as Grassmann algebra. I'm not sure whether there is a single or 2 ends, but okay. Okay, so this is the definition. This is all definition. Okay. Any questions? Any clarifications anyone wants? Yes.
Why haven't we included phi star? Because phi star phi is not the same as phi phi.
It is. It is, no? So it's the same thing. Yeah. So I can generate that by taking a complex numbers minus sign and then get that. So I will not get any nothing new there. Right. Okay. Any other questions? Okay. All right. So what will we do with these kind of things? Okay. So the general game is the following. See, suppose I had a one particle Hilbert space. See, here I had 2 states, 2 one particle states, 1 and 2. Suppose I had a whole set of states. Associated with each one particle state, I will have a phi and a phi star. Okay, that's the game. Okay. So I've made that statement. So now let me try to develop a little bit more things with this. Okay. Suppose I give you a function of Grassmann variable. I have a Grassmann variable phi, and I ask you what is the most general function of this. The most general function of this will be something in the space made out of linear combinations of these guys. So what's the most general function of a single Grassmann variable? Actually, the answer is extremely simple, right? So you just take some number a and take another number b and phi. Nothing else is possible, because if I try to do phi square, it's 0, right? Okay. So what is the most general function of two variables? So there will be 4 things, because with 2 you will get these guys. So just write linear combinations of that, right? So now you get the hang of this, right? So actually Grassmann, the space of Grassmann functions is much simpler than the space of complex functions, for example, right? It's only, see, for example, the function of a Grassmann variable, single Grassmann variable is only linear functions, nothing else. It's already looking very promising, and you don't need to worry about lots of things, okay? So let me ask you the following question to make sure that you have understood what I said. What is e power phi? Sorry? Okay, 1 plus phi, that's the correct answer, right? Okay, what is e power phi star plus phi? Okay, exercise, do this, okay? Do this, important, you should do this, you should do all these things. Okay, I should also keep the time in mind. Okay, all right, so now we have defined functions. After we have defined functions, we were told that we should be differentiating them, integrating them, So there is a set of things that we have done for other functions. So now what we would like to do is, we would like to differentiate this function, right? So what is df by d phi? Take this guy. And what is df by d phi? What is the most natural thing to do? This is a constant, 1, so it doesn't depend on phi, right? There is b, which is a complex number, and phi. So what would you want to do? So the answer should be b, right? Okay. Now, you have to be very careful when playing this game, because suppose I were to take this will look like, a plus b phi plus c phi star, say, so let me say phi 1 phi 2 plus say d phi 1 phi 2, like this. Let's say this function is that. Now you have to be very careful when taking the derivative, because df by d phi 1, d phi 2 will give you a different answer. So if I take the first, let me just use this rule, and if I take d by d phi 2, what happens? This will give me 0. This does not depend on phi 2, so it goes away. So this will give me a c immediately, good. But when I try to differentiate this fellow now, I have to, this derivative has to slide through one of these Grassmann fellows. So I'll pick up a minus sign, right? So what I will get is, I will get phi 1. And then when I take the second derivative with respect to phi 1, so this will be d by d phi 1 of that. This is the result of taking the d by d phi 2, and when I take this will just give me minus c, right? Minus d, I'm sorry. Okay. Yeah. C, d. Okay. All right. Now, what do you think the answer will be for this? Okay, this function is this fellow. I should have called this g or something. Let me just do that immediately. Okay, what do you think the answer for this will be? It will be plus d. Okay, so you see already that these things one has to keep in mind, that you will change signs when you change order of differentiation and so on. Okay, now we have differentiated, right? What should we do next? Integrate. Okay, all right. So now I ask you, what is the integral d phi of f of phi, the one that I have written there? So if you know the answer of two integrals, you will be able to find the answer for that. So you need to know the answer for this, d phi 1, and you need to know the answer for integral d phi phi. If you know that, you can write out the answer for this. So what is the integral of 1? Why? No, you know that. Okay, so you should chill out, right? No, if you have seen it, then then okay. Sorry, right? Yeah, you want it to be phi, no? Because that's what we would have expected, right? But it turns out that's not quite. That doesn't quite work that way. So what do you want this integral to be? You want this to be 0. Ah, okay, excellent. That would be a natural answer to give. But let me see, I want to make sure that what I'm going to say is right. Right? This is 0 and this is 1. Okay, why are we defining it like this? Okay, so this integral, so you have to ask, see, I said that there is a generator, and integration for us is going over some continuous, like integral x equal to 1, 0 to 1 or something. So what does this d phi mean and all that stuff? Okay, so you have to actually generalize the concept of integration as a linear map from the space of functions to numbers. When you generalize that, this is one kind of function on that space, this is another kind of function on that space, and you assign numbers to them. Now, this is assigned number 0 because this 1 is a perfect derivative. Why is it a perfect derivative? Because if I just had this as phi, if I take a derivative with respect to that, I will get 1 as the answer. So 1 is the derivative of phi with respect to itself, and I'm saying a perfect derivative, when I integrate, I'll get 0. Right? Okay, and then I have to assign something to this, and you can choose it to be 1 by convention. Okay, and everything will work. Okay, this is a statement. Okay, it'll get, you don't, I haven't, you don't have to look at me like I committed some, it's fine. Okay, this is all fine, yeah. There's no, that's exactly the idea of a linear map. So this integral is viewed as a linear map from the space of functions on the Grassmann space to complex numbers. Okay, so there's no idea of limit. It's a linear map, right? What do you mean by linear map? That is, I have f1 of phi and f2 of phi, then the answer is sum and so on. Yeah, that was a question. Ah, thank you because I was just going to make exactly that comment. So Grassmann calculus is much easier than the regular calculus because differentiation and integration are the same thing. Right? So Grassmann differentiation and integration are the same. Okay, so this is basically the things I need. Okay, all right. I have to state, yes, there is a question. Okay, I need to make a couple of more statements, and then we are ready to get into the formulation. Okay, so here's the statement. What is the answer for this, if you follow the rules there? So if you follow the rules, this guy is 1 minus phi star phi. So 1 will immediately integrate to 0, right? Now I have to integrate phi, but I have to slide through phi star, so I'll lose this minus sign, and it integrates on phi and it give me 1. And then I'm left with phi star, which integrates with d phi star to give me 1. So the answer is 1. Good? Yeah? Okay. Suppose I change this to A. What will be the answer? A. Good? Okay. All right. Okay, so that's one result I need. Now what I'm going to do is I'm going to introduce one additional property which I'm going to assume for Grassmann variables, which is that if I have some operator, say for example, I have phi I and I have Cj, right? I'm going to say that it is just it's going to anti-commute with even these guys. So when you slide these through operators, you have to put minus signs. Yeah. Yeah. That's I told you about linear map. It is in that sense. Yeah. You don't ask that question, right? When you say it's so for example, if I say integration, it can be viewed as integration on L2, for example, L2 by definition is square integrable functions. That can be viewed as map from some set of functions to linear map. So it's viewed like that. So we are simply, we are lifting the concept of integration and writing linear maps as integration. That's what it is. Okay. So this is the idea. Okay, this is another property that I need. This is an important property. You will see that it will get used very quickly. Okay. So with all these definitions of what are Grassmann numbers and what are the composite numbers that you can construct out of these Grassmann generators and all that, we are ready to actually find a coherent state of a fermionic system. Sorry? C is these operators. Oh, I see that the C is overloaded, no? I see, okay. So sorry. So this C, this is a complex number here. Sorry about that. That can cause confusion. That C is not a, that's a complex number. Yeah.
When you find the Grassmann number here, you slide it through the C1 from phi 2 without changing the sign.
Right. Yeah. So that was to demonstrate that there is a problem, right? No. This was to demonstrate that I have to do something. So once we are done with everything, it will all be fine. Both will pick up minus signs and so on. No. See, if you slide, you'll get minus sign. The other fellow will also get a minus sign. So this will be 0, and then the Grassmann. Everything is fine. Just think about it for a minute. Both. See, what will happen is if you do this correctly with Grassmann, you'll get minus, and the whole thing will become minus. But since this is 0, that minus doesn't matter. So it's okay. My convention will go wrong there, but the final result will all work out fine. You see what I'm saying, right? No. Okay, just think about it. If this happens, you're right. When I do this calculation, when I slide through, I'll just pick up minus signs here. So when I add, this fellow will be 0, and I get minus of that, but that is 0 by definition. So everything is fine. Right? Correct, right? Okay. Okay. So here's the definition of a Grassmann coherent state. Okay. This object is equal to the following. Sorry. Grassmann coherent state is phi minus phi times 1. So what do I have? This is the coherent state. This is the Grassmann variable associated with that coherent state. Associated with with the state, and it is a linear combination of 0 and 1 with this Grassmann number sitting in front of it with a minus sign. Okay. Now I will show you that this will actually give you, it will satisfy this equation. So let me hit this with C phi. So when I hit C with 0, I will get 0, right? And then I have minus C. I hit C. I have phi, and then 1. But now I slide through. When I slide through, this has to become plus 1. So this becomes phi, and this is C and 1 here. But what is C times 1? What is C operating on 1? It is 0. So this is phi times 0. Right? But then this doesn't look right, no? Have I made a mistake? No. But if you just stare here, you will see that a parenthesis will open up, and then you can just put a phi and put a 1 there. Because phi square is 0. You see that? Okay. So you see that this quantity is just phi.
But this is, so this phi is not a state in the Hilbert space.
Phi is a Grassmann number. Oh, I see. Okay, great question. So what you have to do is you have to extend the Hilbert space to not only complex multiplication, but also multiplication by Grassmann numbers. Yeah, I mean you have bought so many things.
But our quantum mechanics is valid for the complex Hilbert space.
Okay, look, I'm maybe the experts can answer this question, but everything will be fine. I mean, let's see. So what I'm saying is, see, Antoine's paper has over 2,000 citations, so it has some correct things. Okay, So this is the definition, and this is basically this definition will be our workhorse. And let me also I have to define some other things. Yeah. So this phi can also be written like this, and if you have seen the bosonic coherent state, it will look very familiar to you, right? It looks pretty much like how you would write a bosonic coherent state, right? Okay. So you can just show that that is equal to that. Okay. Now what I would like to do is I would like to define so if this is a bra, I would like to this is a ket. I'd like to define a bra of that. So that by definition again is the following. It is I just take the conjugate of this. So I have 0, and then I need to flip this guy and do various things. So when I do that, I would get something like this, right? I have to flip and take the conjugate. So dagger becomes this and etc. Okay. Okay. And what is this quantity? This quantity would actually be equal to 0 minus 1 times phi star. Okay. All right. Finally, I need one more. I need actually a couple of more things. I'm going to take a state, some Grassmann variable whose value is psi, and I'm going to take phi, and I'm going to take an inner product of that. Okay. What will that be? Well, you just stick phi here, so you'll get a phi star on here. You'll get, you'll get this phi with a phi here, and then you take inner product. And remember that when you slide Grassmann variables across, you have to change sign and all that. And you will find that this answer is actually something very interesting. It looks like this. Okay, that also looks very familiar because this is also quite similar to what happens in the bosonic case. Okay, good. Okay, all right. Now, what I will ask you is, okay, all these are the set of properties that I will be using repeatedly. I want to ask you a question. What is, if I were to use this complete set of states that I had, which is these state 0 and 1, what is the identity operator in that, in the space? What is it? In terms of the state 0 and 1, what is the identity operator? Correct, exactly, fine. So it is 0, 0, plus 1, 1. This is the stuff. Okay, now what I want to do is, I want to write this identity operator in terms of the Grassmann generator of that state. That's what I want to do. Okay, I'll give you the answer, and you can prove this. And let's not get into, because we'll spend a lot of time. If I get into the proof of these things and so on, then it'll just take up a lot of time. So let me just state the answer. Okay, that's the result. So this is the identity operator written in terms of Grassmann states, the coherent states of the fermionic operator. And this also has, quite strong resemblance to the bosonic case, right? In the bosonic case, you would just get a factor of 1 by 2 pi I here, which does not appear here. But modulo that, it looks exactly the same. Okay, you can even see that it makes sense because you see, because phi inner product would have given me phi star phi, and I'm sort of taking away the length of that vector by doing this. Okay, all right. Okay, good. So suppose I had an operator A on that Hilbert space. Suppose I had an operator A, right? So trace of A would have been what? It would have been 0 A 0 plus 1 A 0. Right? That's what the trace would have been. So what will be the trace in terms of these guys? Okay. Again, I will not prove it. I will just state it, and I hope that I have not made any typos in my notes. Okay, you see there is something crucially different from the bosonic case here. What is that? Yeah, this minus. Okay, this is crucially different here compared to the bosonic case. If you take the harmonic oscillator kind of coherent states and try to do that, you will not get that minus sign. No, no, no. What is it? Oh, no, no. That's a great question. So what is the meaning of this minus? It is not minus of this state. No, that's not what it means. What you need to do is you need to take this formula and hit minus here. Right? So what will happen? 0 will not change. Only this guy will change. Right? It is not minus of that state. It is coherent state with the minus variable. Okay? Good? Okay. So we are done with the formulations that we need. Now I will show you that, we are still, you still have to pay to get something and so on in shops and so on. I will say that the rules of the world have not, the rules of the world have not changed. Okay. So to do this, I will calculate the partition function. So let me take A is equal to e to the minus beta E naught times C dagger C. Okay. So what is the partition function of the system? You can easily calculate that. That is Z equal to 1 plus e to the minus beta E naught. Okay. Just calculate it. I use that formula. Oh, 1A1. Okay, good, thanks. Okay, so this is what happens. Now what I want to show you is that if I use this formula, I will get the same answer. I better get the same answer. Okay, that's what I would like to do. Okay, so what I want to do is I want to use this formula now, use the second formula. So let me write that down. So this is integral d phi star d phi e to the minus phi star phi, and then I have minus phi. Okay, and let me just put a minus phi here. Okay. Now what do I have? I have this operator. Right? If I write this down, I hope that nobody will be offended. I have used the fact that e to the minus beta E naught C dagger C is actually 1 plus e to the minus beta E naught minus 1 C dagger C. Why is that true? Because for fermionic systems, n square is always equal to n. Right? So starting from the second power is same as the first power of n and so on. So all the powers of n will collect out as n, and what multiplies that is e to the minus beta E naught minus 1. Right? And the 1 is the one with no power of n. Right? Okay. Oh, very nice. So now we can see what to do. I hit these guys. When this guy acts on that, what will I get? I will get, when this guy hits that, what will I get? I'll get e to the minus phi star phi. That's this guy. That's this rule. I'm taking this with the 1 and hitting with that. Right? Okay. Now I'll have plus, this is a number, it slides out, it doesn't do anything to anyone. So I'll have e to the minus beta E naught minus 1. C dagger hits on minus phi. What will I get? Look at the definition of, sorry, I didn't write, okay, let me just write that here. Okay, so when it acts on the left, you will get a phi star. Okay, so what I'll get is, when this guy hits that guy, is I'll get a minus phi star like that. And when the C hits this guy, I will get a phi, and actually on the left there is a minus phi sitting, and on the right there is a phi sitting, and they slide through two Grassmann objects. So I will end up getting something like this with no sign change. Right? And this object again is equal to e to the minus phi star phi. Okay? So the final answer after you have done all the algebra is the following. So sorry, I've done all the integrals. The final answer, I'm not yet done the integrals. I need to do the integrals. Yeah, so the final answer is something like this. So I have one of these guys, I have one of these guys, and I have this object. I will show you what it is in a minute. The entire thing will actually become this. That's what it will become. You can show that it simplifies to that. Okay? And let's use that formula which we had there, this fellow. Right? And we are okay? So this is a very long-winded way of doing a trace. Right? Sorry?
It was epsilon and not omega.
Yeah, epsilon. Sorry. Okay. Right? Not too bad. Not great either. Okay. Okay, if that's the situation, it's good. Okay, so we are actually ready to see a path integral. Okay, so let me take I'll just pause here, and if there is any question on whatever we have done so far, now is the time to ask, or hold thy peace forever. What is the meaning of 1 by 5? I don't know. Division is not defined. We don't that's not a question we ask. You want me to write the expression for minus 5. Just put minus 5 here. So you'll just get a plus. Yeah. Other questions? Any other questions? Okay. So if that's clear, we are ready to actually see the first path integral. Okay, what are the rules I need? I need this guy. So let me hold on to that. I don't need any of this, so let me just erase this. Okay, so let's start with this partition function, which I will write this in this form, which we have just seen gives us the correct answer, e to the minus phi star phi, and then there is a minus phi, and then e to the minus beta E0 C dagger C, and phi here. Okay. So this is the exact formula that I just showed you, gives us, if you do the Grassmann integration, the correct answer for the partition function. Okay. Now I will show you that this object can be written as a path integral. Okay. Okay. So the first thing to realize is that this object you can view as a function defined on 0 to beta, and you are looking at the function at beta. You can sort of visualize it like that. Okay. So what I'm going to do, I'm going to, because I want to do some multiplications later in a certain order, I'm going to draw my axis this way. So this is 0, this is the tau axis if you like. This is the tau axis, this is 0, and this is beta. Okay. I'm doing this because the order of multiplications are important, so I have to keep track of that. That's all. Okay, so what I'm going to do is I'm going to split this into n intervals. So this is interval number 1, this is 2, and this is the nth interval. Everybody's okay? All right. Then what I'm going to do, I'm going to write e to the minus beta C dagger C is equal to product over all these n intervals. So this is, let's say, the nth interval. this is the n minus 1th interval. You see I'm going this way, right? And this is the n plus 1th interval, right? And I'm just going to just write it like this. Let me just, okay, epsilon 0, just call this h if you like. H, and let me just put an n there. It's the same thing. The h is the same. I'm simply putting an n so that we remember that it's in the nth interval. So all I have done is I've taken this beta and split it up, just diced it up into delta tau. That's it. And I'm perfectly allowed to do this because they're all, the C dagger C is same in each slice, so they commute with each other. So e to the a, e to the b is e to the a plus b. Right? Because everything is commuting and we don't need to worry about anything. Good? Okay, all right. So let me just write this as a product now so that you will see. So here there is a e to the minus delta tau h, 1 let me say, e to the minus delta tau h2, they are h1 and h2 are actually the same thing. I'm simply writing it like that, okay? And if I look at this guy, for example, there is e to the minus delta tau hn and h little n and so on, this interval. There are these guys, okay? And what these guys are being sandwiched by, there is a phi sitting here, coming from here, and then there is on the e to the delta tau hn, there is a minus phi sitting here. Okay? So by now you will know what I'm going to do. I've already given a little space here, so you have to stare. So when you stare, what will happen? You will get a identity showing up there. Right? So you will get an identity showing up here, and you will get an identity showing up in between each one of these guys. Correct? I'm going to get an identity in between each one of these e to the delta tau hn. Okay? So now, because I'm going to get different identities, and the identity is going to be written as an integral, I need some notation. Right? So the identity I'm going to introduce between 1 and 2, so this thing I'm going to write in terms of variable phi 1. So something between n and n plus 1, so let me just write between n and n plus 1, so this guy will be called as phi n, like this. No, between 1 and 2 this will be phi n minus 1, and so on. Okay? Alright. So if I want to introduce an identity, I have to do two things. I have to have this guy, and I have to have this guy. So remember, this guy is quadratic in these numbers. So anything that is quadratic, you can freely slide, right? Because it's two Grassmanns. So if it slides past anything, it will pick up the 2 signs, and then you are fine. So you can slide all of these guys, right? So what I'm going to also do is this last fellow, which is minus phi, I'm going to call as phi n by my convention. Okay. So what am I left with after I have done all this? I'm left with the following. I'm left with this. Good? Everybody's okay? Good. Okay. So now we know what this object is. Right? What is that object? That is phi n, and I have this I can write as 1 minus delta tau epsilon 0 c dagger c, and then phi n minus 1. So what happens to this? This will give me, this guy hitting on that will give me phi n star, and that guy hitting on this guy will give me phi n minus 1, right? Okay, I'll write down and you see whether you like it or not. Phi n minus 1, 1 minus delta tau epsilon 0 phi n star phi n minus 1. Any questions? Okay. What is this quantity? Use that formula that we have up there, this guy. Right? So this guy will be e to the phi n star phi n minus 1. And what is this guy? It is e to the minus delta tau epsilon 0 phi n star phi n minus 1. Correct? All of these are quadratic in Grassmann numbers. So you can freely slide them whichever way you want. Okay? So now I'm ready to put everything together. Right? Collect everything together and rewrite it like this. Yeah? Did I make mistake? Okay. But just take delta tau to be very small. Then that epsilon e to the delta tau minus 1 can be expanded as that and so on. Take delta tau to be, take the small delta tau limit, which is fine. Yeah. Okay, so this is the equation. Good? Okay? Everybody good? Okay. What do you see here? Well, if you do a little bit more work, what I can do is I can just rearrange this stuff a little bit. So what I'll do is I'll take this out like this, and I'll make this. This is minus sum n. I have a delta tau, I take it out, and I divide this by delta tau, and then I just leave this here, and I have this. Yeah? Good? If I take the n going to infinity limit, capital N going to infinity limit, what will I get? This will become an integral, and these set of all phi n's, right? So you can imagine that there is some phi 1 here, phi 2 here, and so on. That sort of becomes a function, right? That sort of becomes a path. So let me just draw that here. So just schematically, I'm saying there is phi 0 here, and then phi 1, and so on. So this becomes like a path, except that this path has an interesting characteristic. Wherever you start with phi 0, it has, when you reach phi n, that has to be negative of phi 0. Because phi n was always equal to minus phi 0. So these paths are in some sense, when they go around and come back, not come back, when they start at 0 and reach beta, they will, whatever they started off with, they will reach the minus of that. Right? So this is a path, this thing in the n going to infinity limit. Okay, let me just write it there. In the capital N going to infinity limit, the exponent is an integral 0 to beta, let me call that as S, d tau, I say phi star tau, d by d tau, phi tau, plus epsilon 0 phi star tau phi tau. And this condition, the condition is that these paths, so the partition function itself will be integral over all these paths. We'll just symbolically denote the measure of integration like this, e to the minus s functional of these guys, which is what I've defined here, this guy. And this is defined on all paths which satisfy the following condition: phi of beta is equal to minus phi of 0. Okay? Yeah?
how can you replace the sum by the integral for Grassmann numbers?
The one I can use this.
No, integrals were defined in a kind of ad hoc way for the Grassmann.
No. Okay. I understand. This is not an integral over Grassmann variables.
Oh,
This
yeah.
is an integral of a function whose Grassmann valued, but the domain of the definition of the function is imaginary time tau, which is a real number. Right? These are Grassmann valued functions. So this axis is Grassmann numbers. This axis is real number tau. Yeah? Okay, other questions? Yeah? Okay, good. All right, now I have a question for you. Is there anything here that you have seen before? My claim is that there is something here that you have seen before, which will be very helpful in reading papers, etc. I will rewrite this in a more suggestive way and then ask you to identify it. Let me take this action and rewrite this in the following fashion. Inverse of Green's function, right? Not Green's function yet, right? It's inverse of Green's function. In fact, I can write this in a much more interesting way to make it look like a, you will see what it will look like, just a minute. Right? And remember what this was. Yesterday we actually derived this yesterday for such non-interacting particles. This object G inverse tau minus tau prime is equal to d by d tau plus epsilon 0 delta of tau minus tau prime. Okay, so somebody had asked me, like, why am I trying to find the equations of the Green's function and so on, right? And here is the answer. So if you formulate it in the path integral framework, you will get a classical action for the fermions. This is the classical action. This is fermionic classical mechanics right here. So what you can do, so this is the Lagrangian density, right? From here you can actually calculate a Hamiltonian for the system. You can actually calculate Hamilton's equations of motion, and you can actually show that this does exactly what a harmonic oscillator should do. All in classical mechanics. So just write a Hamiltonian, and the important thing here is, when you take derivatives d by dp, etc., that kind of stuff, you have to make sure that this ordering of operators, the ordering of these numbers are respected, and you will see that everything works out very nicely. Okay. All right. So any questions at this point? How many of you are simply sort of switched off? Oh, that's almost everyone. Okay. Me too, looks like. Okay. All right. Okay. Yeah, I admit that this is not the most interesting stuff, but okay. All right. But it's probably useful stuff. Okay. All right. With that, discussion, let me switch gears now, and let me try to write the Hubbard model as a path integral, the partition function of the Hubbard model as a path integral. Right? Yeah? This one. Yeah.
A Grassmann integration.
This is a path, yeah, it is a Grassmann integration. This integration will be a Grassmann path integration. Whereas this thing, the action is the integral is on the tau line. But this is a Grassmann path integration, yes.
If we view phi star as an independent variable, such as phi star of minus beta should also be equal to minus phi star of beta.
It is there. Yeah. I'm not being very precise, but it's there.
You said that a Grassmann integral is just a map. So how do you define a path and?
Okay. I don't know. Okay. So all right. So what? So again, so you have the space of Grassmann variables. So there's something called Grassmann space, right? Okay. So you're asking me like how many how many Grassmann variables are there in that?
As in complex numbers, you have axis,
right,
and you don't have that anymore over here.
The path is Grassmann valued, and the path, this thing is parameter is a real kind.
No, he's asking like what is, see for example, complex numbers can be viewed as a two-dimensional plane.
Yes.
So suppose I give you this Grassmann number, which I'm integrating over.
Yeah, you can't visualize it. That's
Okay, I don't try to visualize it. I try to write papers. Sorry? Exactly. Yeah, I really see your questions are well taken. I don't know the answers. Yeah. Okay, other questions? Okay, if not, let's do the Hubbard model. Okay. Okay, so what is the Hubbard model? Let me just write the Hamiltonian here. Right? So the Hamiltonian is just the usual thing. I have some lattice, and then I have this, and I have the interaction, which is some kind of on-site, not some kind of, it is an on-site repulsion. Okay, so this is the Hamiltonian. Okay, now to do this, what do I need to do? I need to go to every site, right? So this is my, so imagine that I have some square lattice. At every site, right, I put 4 Grassmann generators. At every site, I put 4 Grassmann generators. What are they? So just go to this site. Phi I up, phi I down, phi star I up, phi star I down. Right? That's my state. I mean, that's the set of Grassmann numbers that I'm going to use at every site. Okay? So now, if I have this definition, can you tell me what will be a generic coherent state of with Grassmann numbers of the many body coherent state? No, not summation. That's not, okay, product you can think of product, but appropriate product. So what I'll do is, I will define something like, phi 1 up, phi 1 down, and so on, like that. Right? It's like you had occupation numbers, right? So you had put 0 and 1 at each site of each one orbital place. Those were your slated determinants, for example. Now wherever you're putting 1 and 0, don't put 1 and 0, put phi I, whatever the spin label there. Those are the set of coherent states of the system. Got the point, right? Okay. So suppose I were to hit this guy with C I sigma. What will I get? What will be the answer? Sorry? Correct. Okay. So this will be phi I sigma. And now what I will do, I will simply write this as a collection like this. Just as a collection. I don't write explicitly each one of them. Everybody's good? Okay, very nice. Okay, so now we are ready to play the game. So now we know what is the partition of identity or what is the identity operator in this space. So this will be product over all of these guys. Right, product over all of these guys, e to the minus summation over I sigma phi star I sigma, phi I sigma, phi I sigma, with a minus sign, remember. No, this, the identity will not have the minus sign. Okay. That. So that's the identity. Right? What will be the trace of an operator? Trace of a many body operator. It can be anything now. Right? This quantity will be everything same until here. This is all same. Right? And this fellow will become minus phi I sigma A phi I sigma. That's what I'll get. Okay? Okay. So now you see I can do exactly the same thing, and it's very easy for me, right? What will I do? I will just come here, I will put some n superscript here, and then I'll do I sigma. I've split beta into all these things, etc. Right? And then this will be I sigma and n, I sigma like that, and then here I will have the following. Like that, okay? And this will be some set of objects like this. Okay? There will be a set of objects like that, right? Everybody's okay with this? Okay? And now, of course, I have to not have all these things. I will change it a little bit. Okay. Now it turns out that in going from here to the next step, you have to make one more little trick. So what you have to do is, this is an operator. So that operator will have several terms, right? So it has minus delta tau. So for example, it will have a C dagger C kind of term, and then it will have a C dagger C C kind of term coming from this guy, right? When you expand this in power series, what will I get? I'll get minus delta tau times the same thing here, and then I'll get something plus delta tau square times something. Correct? This one has to be handled carefully. The reason is, when I want to do the path integral, what I want to have is, I want to have all the C daggers to the left, which will act on the left side guys, these left coherent states, and all the C's to the right, which will act on the right coherent states. That's what I want to do. But my operator is not in that form. So what I do is I replace this operator by what is called as a normal ordered version of it. That is, I take this operator and replace all the C daggers in any expression to the left and all the C's to the right. I do that. What is the error I will make? I will make an error of order delta tau square, because I already start off with something normal ordered. The first thing in which I'll have to make a change will be at delta tau square. Okay, and precisely your question comes here as well, right? So I'm going to take delta tau going to zero limit, so I don't mind. Okay, all right. So once you do that, okay, I leave it as an exercise for you to show that this fellow will be simply wherever you see these C daggers in that equation, replace them by the appropriate phi star n's. Wherever you see C's in that, you replace them by phi n minus 1. And just play the game, right? You will find that the partition function is this. Again, I need this condition. Okay, now what is this S? Of course we can derive it, but I'll tell you what is the rule to write down S. It's very easy. Just take the Hamiltonian that you have and take all the set of Grassmann generators that you have. Just write it like this. So S will be equal to integral 0 to beta, okay, d tau, that of course follows, sum over all the Grassmann generators. So what will you get? You will get this term. You will get this, just like what we got there. And then you take the Hamiltonian, wherever you see C dagger, write phi star. And wherever you see C, you write phi. That's it. So this will be minus T sum phi star I sigma. This is a function of tau. Remember, all of these are functions of tau now. Okay? Phi j sigma tau plus, let me call this as GC. This is Grassmann conjugate. Right? Okay? And then the remainder. Okay, and now again I want to emphasize that this is the equation that Antoine has shown in this paper. And in fact, I had shown you precisely this. So I have to also tell you that Antoine actually does not use phi's, he does not distinguish between the operator and this. It's a very simple, it's much simpler to, after a while not to have too much notation around. So what is done is the variable C itself is used as the Grassmann number rather than an operator, right? So it's simpler, you don't have to carry a lot of symbols around. Okay, so this is the action. Okay, so one of my promises have been redeemed, which is that I told you that I will show you the path integral formulation, and that's what it is, of the Hubbard model. Okay, so this is, so we have reached one milestone. Okay, now we have to do some physics. Yes?
So can you repeat on the point, how does normal ordering lead to a error of delta tau square?
Okay, all right. Okay, so suppose I take this guy, right? What do I want to do? I want to have 1 minus delta tau, and then there is a C dagger C plus C dagger C C. This is the linear term in this, right? And then I will have a quadratic term, which is delta tau square, open bracket. Then I will get C dagger C plus C dagger C C multiplied by C dagger C plus C dagger C C. This is what I want to do. And suppose I take this guy with this guy, I have to normal order it. So when I normal order it, I will flip the C dagger through the C, which will give me 1. That 1 will multiply with delta square, which I am going to throw away. So I have lost something of order. Yeah.
So on every side you had put 4 Grassmann generators.
Yeah, 2 and 2 conjugates.
And when you are constructing the many body state, using them, you're using only the, let's say, unconjugated ones.
Where are the conjugate ones you're asking?
Right.
So so if these are the kets, they're the appropriate browser there, right? Like I define states like this. I defined this, right? Yeah, so they are there.
And one more remark, just, it's
Yeah.
very hard to see from here, that's why I want to clear.
Oh.
The Z you had written on top there
Yeah.
is a D phi I sigma star,
N, this is N.
N, and that is M.
No, that is also N.
Okay.
Yeah.
Yeah, so discretization.
Discretization in time.
Huh.
Yeah. Yes.
when you are discretizing in time,
Ah,
now the Hamiltonian, is it committing itself? Because
what do you mean? I did not understand the question.
because you are multiplying e to the power a into e to the power b into e to the power
Oh,
c.
excellent question. Okay, okay, very good question. Thank you. Thank you. So what is being asked is the following, right? So what is being asked is that I had e to the minus beta h. H has the kinetic energy piece and the interaction piece. So question that's being asked is, first I will take your question and I'll ask a question to you. Do these commute? So you think they don't commute, right? Yeah. So these see this, any number state, any number eigenstate is actually an eigenstate of this, but it's not an eigenstate of this because it will mix the number states. Okay. So we know that there is some non-commutation around. So then the question is, if I take this thing and write it like this, am I not making an error? The answer is yes, I'm making an error, which is again delta tau square. So that's called a Trotter error. So it's well known. Yeah. Sorry, I should have said that, but I didn't. Okay, thank you. Yes, Abbas.
Itself, so I should be able
Here
to.
it is fine, but no. Yeah, here it's fine. So, but if I had some, so that problem will show up when you do like if you put p when you do path integrals and do p on one side and x on the other side and do mixed path integrals and all. Generically, there could be a problem, and then you can use this. Yeah. Okay. Other questions? Yeah. Oh, a little further down or? Okay. All right. So I just want to make two more comments regarding path integrals. The first one is, suppose I have a path integral, how do I actually calculate anything, right? So I will start, I will just say, I will just modify this and then everything will be okay. Okay, so let us take this guy, and how will I calculate this? Okay, so the rule to calculate this, I'll just state that as a rule. It's the following: you do sort of ratio of two path integrals. So I will write everything now. Here phi means the collection of all those guys and so on, right? So this is e to the minus s phi star phi, and then I have a tau and b tau prime divided by the partition function, which is the same thing. Okay, so this is the final result. Okay, now you may ask, where did this t tau go in here? I have not done anything about t tau. You see, I have just simply ignored it. Okay? Sorry? Right, exactly. So that's absolutely correct. So the remarkable thing about path integrals, no, not remarkable, the nice thing about path integrals is that they're automatically time ordered. Because the way you constructed this, you see, you put stuff. So where will I put b tau? So when I took my interval, I split it up into various slices, right? So suppose this tau prime were here, I will put the b tau here, right? And this tau over here, I will put the a there. So it's automatically time ordered. You don't need to do anything special to do further time ordering and all that, right? So you get time ordering for free. Okay. In fact, if you read Feynman's article, the one it's called some space-time formulation of quantum mechanics, he will actually show you that the uncertainty principle, that xp commutator is I, will actually come from this time ordering business. It's very beautiful. You should read that. Okay. Okay. I want to make one more comment. So you recall that I discussed a problem in cold atoms in which I had made a notational error which Manoj had pointed out. And I had written a Hamiltonian for this. This is the Hamiltonian for that system. Okay, this is what I had done.
The minus sign in the RHS.
Yes, I have missed a minus sign in the RHS, this is correct. Yeah, time ordering goes away, minus signs don't. Okay. Okay. So can you tell me, of course I should be able to write this as an action, e to the path integral over some action. What is that action? So this will eventually be written, the partition function of this guy can be written as okay, this is just symbolic. Okay, this is true. So tell me what is this set of objects that are going to go here? What are the paths and what is the action? So when I had Hubbard model, what did I do? At every site, I introduced 4 generators, one for up, one for down, and their conjugates. So if I have a continuum, what should I do? Discretize the continuum. Okay, that's all fine. So at every point in space, I attach a set of 4 Grassmann generators, exactly the same way. So that these guys will be actually phi sigma of r, phi sigma of r, and of course in the path integral they will also depend on tau. Right? So now you are asking how to visualize this. So imagine that there is some axis you can draw. So imagine it's 2-dimensional space. So at every point in the space, there is some fiber that is being attached, right? And that fiber has a Grassmann variable on it, actually 4 of them, right? So a field configuration is a section of this, right? That's the classical field of fermions. So it's a function, it's Grassmann function like this, okay? All right, and what is the action? So it's a function of this function. It's a function of this. Very easy, right? Just stick this integral 0 to beta, right? So this goes from integral 0 to beta d tau, right? So this is over some volume. So this is integral over volume ddr. And then what will I have? I'll have this kind of terms, right? I will just write this h, take h, what I have written here, and wherever you see c's, you replace them by phi, and wherever you see c dagger, replace it by phi star. So it's become some functional of that again. I'll just write it like that, and so on. Okay? And this is the partition function of that. Right? Now I will tell you something, if you have not heard before or seen before, should be pretty interesting. This partition function now is a partition function of a classical system in one additional dimension. What is that additional dimension? That is beta. So if you want to visualize, what has happened is, if this thing is volume V, right, in d-dimensional space, I have added one more dimension. So I have now made this problem into a problem in one additional dimension, so that what is that? That is beta. So volume of this d+1 dimensional space is V times beta. Right? So it is V times beta. So this is a d+1 dimensional space. So here's a very interesting statement. A d-dimensional quantum stat-mech problem is equivalent to a d+1 dimensional classical field theory. Okay, classical field theory. This is all classical. Okay, and this idea is used extensively in computation, etc. So several quantum Monte Carlo ideas actually use this, and you can. So the point is that you can do classical simulation of quantum problems. Okay, all right. Which delta by delta phi?
The first term in that I don't really understand.
Oh, it's a mistake, no?
Okay.
Yeah. Yeah. Oh, I thought you were going to ask a question. Okay. Okay. So you see the splash, right? So this is the statement D equal to D+1. D classical, D quantum is equal to D+1. Okay. And it actually, so if I go to 0 temperature, this statement actually has many other important significance, like what if I have a quantum phase transition that could correspond to a classic phase transition of some classical system in a higher dimension and so on. Okay, so there are some nice things that will come out of this. Okay, any questions? So my formulation assignment is over. Okay, I'm itching to start doing some real physics now. Right, this is all formulation. It will help us to do calculations. We have to now take an example and use these techniques and learn some physics. Okay. So Indra, maybe I will start that. I have 3 more minutes. I'll start it after the, yeah, because I think it's a good time to break. Yeah. Yeah. Okay. I can tell the phenomena. Okay. I can tell you about the phenomena. Okay. So so there is a very important and interesting problem that intrigued a lot of physicists in the 1950s, and it is the following. You take some nice simple metal like copper, right? So I have a block of copper, right? And put a little bit of some iron or manganese or one of these guys, which are supposed to be magnetic ions, right? I'm sure you have seen some of these things in this in the school, in other talks, etc. Okay. All right. So I just put a few of them. So this could be, parts per million, a few parts per million, maybe 10 parts per million, something like that. It's very small concentration of these guys. Okay. Now I ask you the following question. I have temperature, and I'm going to measure the susceptibility of the system, magnetic susceptibility of the system. Okay. Let's just assume that copper is a simple metal without any complications. If I did not have these magnetic impurities, what will this curve look like? Sorry? Somebody said straight line. That's a correct answer. The question is, what is the slope? Constant. Thank you. That's correct. So it will be constant because typically we are well below the Fermi energy, and then there's no dependence, there's no significant dependence of temperature dependence of susceptibility. Okay. Now what do? I know that there is a background constant susceptibility. I measure the magnetic susceptibility and subtract this out of that. Okay. So now whatever I am going to find has to be because of whatever else is creating magnetic responses. Right? So for example, it could be these iron fellows that I've added. Okay? So what is found is something quite interesting. What is found is that the natural thing to do would be 1 by chi. You will find that it's linear, which is telling you what? Sorry? Curie, but what is it telling you? If you say that, no, why did you say Curie and then Curie wise? No. Okay, just let's hold on to Curie. So there is, just 1 by chi, and it's going linear in T. What is it telling you about the system? Sorry? Paramagnetic. Okay. What I want from you is that it is forming moments. So this iron is actually forming a moment inside. So it's quote unquote dissolved in copper, but it's still holding on to its moment. Nothing has happened to its moment despite being dissolved in copper. Okay. Okay, now the interesting thing is, very nice, so it looks like fully formed moments here. But as you come down in temperature, what would you have expected this to do? If it continued to hold on to this moment stuff, it would just go straight to 0, because it will be Curie. But what happens is it doesn't go to 0. It sort of deviates from this. So what does that mean? That means at very low temperatures there are no moments. Because had there been fully formed moments, they would have given you 1 by T susceptibility. It doesn't blow up, it goes to finite value. 1 by chi I am plotting. So if you plotted chi, yeah, then and it were fully formed moments, like a simple paramagnet, it would have gone all the way to infinity. Now here it's going to some finite value. Okay? And this happens at some temperature. Okay, I will just call it Tm. There is a reason why I am calling it Tm. Okay. Now copper is something that you can very easily experiment with, right? So you could stick leads onto it, you can measure current, voltage, you can do various things. So you certainly can measure resistivity, right? So suppose I were to measure resistivity as a function of temperature. At high temperature, what will be the resistivity of copper? High temperature meaning high compared to what? Like Debye temperature. Sorry? What will be the resistivity? Straight line, linear, right? And then if you come down in temperature, what happens to the resistivity? It decreases, of course. That's being metallic, it will decrease. But how does it depend on temperature? It will go as T power 5, yeah, and so on. Now what happens? So there is some linear T. There is a T power 5 regime, and then just around this temperature, what happens? It does an upturn like this, and then it goes to some value. Okay, so it turns out that the people who did experiments, I was reading a very nice article in, or the chapter in Hugheson's book on kondo effect. There is a nice history of the kondo effect, and there are some early people who thought that this actually shows violation of Matheson's rule, because they thought, we have different scattering mechanisms, so the 1 by tau should add and so on, and they thought that there's some problem with Matheson's rule. So, and they in fact wrote papers as such, right? So this is quite remarkable, right? That it goes down and then it goes up, right? So you may think, this resistivity in this regime is actually going down with temperature. So has this become like a semiconductor, right? Okay. Now there is this Tm, and very interestingly, Tm goes as C power 1 by 5. What is C? C is the concentration of the impurities that you have. Okay, so this is the phenomena. Okay, so I have some system where I have fully formed moments at some high temperature, and as I cool it down, they seem to vanish. Not only they vanish, they produce very unpleasant effects, like resistivity going up with reducing temperature in a metal, right? So we would like to understand this. Okay, and it turns out that understanding this problem is sort of turned out that it has very important consequences for many things. And as far as this school and the remaining lectures are concerned, the resolution of this problem introduced a certain model which we will study in the next meeting. And it turns out that that model has everything to do with taking the Hubbard model and making a DMFT formulation of that. Okay, so we will look at what that model is, and I will of course not derive everything in great detail. I will do some work and get to an action of the impurity problem in the way that Antoine presents in his paper, and then once I get there, I will have some qualitative discussion of what the physics is, And then that will be the end of my part of the discussion, and I'm sure it will be taken up in greater detail in the school and other lectures. Yeah. Okay. Oh, I've taken 5 minutes more. Sorry. Okay.